Hello, welcome back. Good afternoon and welcome back everybody to the final keynote of .NEXT 2019. I hope you've had an amazing few days and thank you for spending so much time with us. As you just heard, WEURSSA, catchy, Western Europe, Sub-Saharan Africa. I'm here now exactly 4 months. And can I just say what a privilege it is to work in this great company, but moreover, to support and serve you amazing customers and partners. So thank you for everything that you do for us. So I know a few of us had quite a late night last night. So I'm going to do, this morning the energy was a little flat, as expected. So I'm going to do a quick energy check. And this is for the countries in my region, just to give you a warning. So I just want to, first we're going to have a shout out for every customer, Nutanix partner in the United Kingdom. Let's hear from you. All right, good. Not bad. Slightly smaller audience, and now to hear from Ireland. Hey! Sorry. He was set up to do that. I think any South Africans left? I think South Africa? Yeah, there we go. And finally, I'm going to group these 4 countries in my region, a little smaller in terms of representation. Nigeria, Ghana, Kenya, Ethiopia. Are you out there? All right. Okay, thank you. So listen, I hope you had a great conference. I've had an amazing first .NEXT for me. And one of my highlights was actually, it's not a Nutanix thing, so sorry, Diraj, Julie, but it was Tuesday night dinner. A number of our customers had a guest speaker, Tim Peake. So Tim Peake, I'm sure you all know, is a British astronaut. He spent 6 months in the International Space Station and told us an amazing story of human endeavor that I won't have time to cover here. But the thing that really stood out for me was when it came to Q&A at the end of this amazing journey he'd been on. And one of our customers, Justin Fielder, our CTO for one of our great MSPs, Zen Internet, asked a great question, which was, when you came back down to planet Earth after the journey you'd been through, what did you think and what was your perspective on the environment and what we were doing to the planet? And we were kind of expecting, you know, a sort of downbeat, slightly depressed, what are we all doing? But his answer was enormously positive. And the thing he said was, you know, the sun generates 7,000 times the amount of energy this planet needs to run each day. And that is an enormous opportunity for scientists, for technologists, and for this community to collaborate on that particular problem. So he had this enormously positive outlook on what can be quite a negative thing in the press. So for me, that sort of kind of was a great representation of this T-shirt, which is themed here, the dreamers, the builders, and the believers, you know, and he's clearly one of those. So that was really sort of landed for me. So look, my job here is really easy. It's just to introduce our 2 final and very special guests. And first, I'm very humbled to say that shortly I'll be inviting Dr. Katie Bouman to stage. At only 30 years old, Dr. Bouman has already achieved more than many of us will in a lifetime. A fellow of MIT, a TEDx speaker, Dr. Bouman is best known for being part of a team of 200 researchers who led an amazing feat of modern science and international collaboration, leading to the first ever image of a black hole. Dr. Katie Bouman will share with us how the creation of a new algorithm, a computational Earth-sized telescope, 5 petabytes of data, and 4 teams collaborated to bring the black hole image to life. And this has recently been awarded with the Breakthrough Prize in Fundamental Physics, a $3 million prize. And afterwards, to close .NEXT, and to mark the first time my wife has ever been jealous that I work in IT, That's right. Winter is coming. Emmy Award nominee for Outstanding Lead Actor and Outstanding Supporting Actor, former Game of Thrones star Kit Harington will close .next with a lively discussion around growth and disruption with Nutanix SVP of Corporate Marketing, Julie O'Brien. Now, before I introduce Dr. Bouman, if you're a first-time attendee, please make sure you stay until the end after closing comments from Kit, because we have a few very special surprises for you. So without further ado, please join me in a very warm .next welcome for a true inspiration, Dr. Katie Bouman. She is coming. Here we have Dr. Bouman. Is this a setup? Yay!
Sorry. Thank you. Oh man, it's wonderful being here. This is amazing. So earlier this year, a blurry, perhaps aesthetically unpleasing image graced the cover of newspapers from around the world. You may have seen this picture. It was the first image ever taken of a black hole. And this image swept the world. It's estimated that billions of people saw this ring of light surrounding a supermassive black hole. Scientifically, with this image, we had achieved a huge milestone. We had shown that it was possible to take a direct image of the environment around a black hole and use it to probe our understanding of gravity. Humanity had taken a picture of something that they believed, was maybe impossible, and that, I think, really captured people's imaginations. But as inspiring as this image is, I find this image of the team of people who made it possible just as inspiring. The black hole image was the result of the hard work of over 200 scientists from around the world, astronomers, physicists, mathematicians, and engineers who worked together to achieve something not possible for any one person to do. To do this, we brought together people from continents around the world, North and South America, Asia, Africa, and all across Europe to make this picture a reality. And so today I want to tell you a little bit about how we were able to work together to take the very first picture of a black hole. So black holes are some of the most mysterious objects in the universe. They're cloaked by an event horizon where extreme gravity prevents even light from escaping them. Yet the matter that falls onto a black hole is it's superheated to hundreds of billions of degrees so that before it passes through the event horizon, it shines very brightly. And for that reason, although black holes are relatively small compared to the size of galaxies, they can outshine the combined starlight of all the stars in their host galaxies. And so scientists have been studying black holes ever since they were first predicted from Einstein's theory of general relativity just over 100 years ago. And in particular, for decades, scientists have been studying the giant elliptical galaxy at the head of the Virgo constellation. So this galaxy, called M87, is 55 million light years away from us. Years ago, someone discovered a streak of light, a galactic-scale jet of plasma that was shooting out of the heart of this galaxy and marking the spot of a supermassive black hole. Ever since then, for decades, scientists have been building better and better instruments in order to study this jet and the supermassive black hole at its core. And in April of 2017, an Earth-sized telescope hooked together and collected the data necessary to make the first image of a black hole. And 2 years later, after processing the data, this is what we saw. But how are we able to take a picture of something that, by definition, doesn't let light escape, so is unseeable? Well, light propagating near a black hole doesn't follow straight lines. Because of the extreme gravity around the black hole, it actually bends the light. So photons can even go in complete circles around the black hole. And so as I said, around the black hole, we have this gas that is really hot, and so there are these photons flying around everywhere. And some of these photons fall into the black hole, but other ones just graze it and are bent by it, such that the net effect is that the black hole bends them into this circular shape. In effect, the black hole is basically casting a shadow on a backdrop of this hot material. And this is often referred to as the black hole shadow. So if Einstein's theory of general relativity was correct, the size and the shape of this ring would tell us about the mass and the spin of the black hole. And scientists who've done simulations of the plasma around a black hole predict that if we were able to see at about a 1 millimeter wavelength, and we had infinite resolution glasses, we would see something like this. But even if we can see, the environment around a black hole, even if this is lit up in this ring shape, taking this picture is incredibly hard. There's a number of reasons why that's the case, but one of the biggest ones is that this ring is about 40 microarcseconds in size, which is about the same size as a grain of sand, but when you're viewing it, when the grain of sand is in New York, and you're viewing it from the Nutanix headquarters in San Jose. So it's incredibly small, and taking a picture of something that small is really hard. So if you plug in the necessary angular resolution and wavelength into a diffraction limit equation that tells us how big of a telescope we need to build, it turns out that you need to build a telescope that's 13 million meters across, or essentially the size of the Earth. And if we could build this Earth-sized telescope, we could just start to make out that distinctive ring of light that's indicative of the black hole's event horizon. OK, well, although building a single-dish telescope the size of the Earth isn't possible, I've been working as part of an international collaboration called the Event Horizon Telescope that built the first computational telescope capable of resolving structure on the scale of a black hole's event horizon. And in this computational telescope, we have disjoint telescopes located around the world that work together. So at each site, we have teams of researchers who go out, and they basically freeze the data onto petabytes of hard drives. And by using the precise timing of atomic clocks at each of the sites, we can then bring the data together and process it in our computers in order to make that picture. So my primary role within the project was on working on constructing the image from this data, so designing the methods and techniques that we use to make that image. So how do we do that? Well, unlike with a regular camera, we don't actually capture the picture in pixel space. Instead, we capture it in frequency space. So we essentially take measurements of the black hole image's Fourier transform. If we had put telescopes all over the globe, if we tiled the globe in telescopes, we would measure all these spatial frequency measurements. But because we only have telescopes at a few locations, that means that we only see a few number of measurements. And it turns out for every 2 telescopes in our telescope array, we get a single measurement of the underlying image's 2D spatial frequency that's related to the projected baseline between the telescopes. Each of these points that we measure has an amplitude in a phase, OK? But even out of those 8 telescopes that observed in 2017, actually only 5 of them were at different locations and could see the black hole in M87. So that would only be 5 choose 2, 10 measurements that we'd have to use to make an image from. But luckily, as the Earth is rotating, we actually get new measurements. So since the baselines between telescopes change as the Earth rotates, this amounts to carving out these different elliptical paths in that spatial frequency plane. So what do these points tell us? Well, the closer 2 telescopes are together, the smaller that baseline, and so that's going to measure low spatial frequencies. And so that tells you about broad structure in the image, large-scale structure. So to get the fine detail we need to see that ring, we have to put our telescopes as far apart as possible. So if you're unfamiliar with what the Fourier transform of an image is or what these measurements mean, I like to think of it a bit like this. Each measurement that we make is a little bit like a note in a song. And a measurement at a different location corresponds to a different tone, a different note. And so watching the Event Horizon Telescope, watching the black hole with the Event Horizon Telescope is a bit like listening to a song being played on a piano that has a lot of broken keys. If there's enough keys that are working, you can still often make out what the song is being played. OK, so at this point, we have all this data, this sparse data we've collected, and we can kind of abstract away the astrophysics and think of it as a mathematical problem. We just have to find the image that caused it. OK, so if we were given measurements, again, that covered the whole frequency plane, it would be trivial. We could just take the inverse of these measurements to get an image. But because we only have a sparse number of images, a sparse number of data points, that means that there's actually an infinite number of images that perfectly explain the measurements we've seen. Just like in the piano analogy, the notes that are broken could be played in an infinite number of ways. And on top of that, the fact that there's a different, quickly changing atmosphere above every telescope makes the data that we do see incredibly noisy. And I just want to give you an idea of why it is so noisy. So the whole reason that the Event Horizon Telescope is able to work is due to the fact that light from the black hole is going to travel to Earth for 55 million years, and then it's going to reach one of the telescopes slightly before the other one. And that time delay is the key thing that allows us to extract the 2D spatial frequency component used for image reconstruction. But when you have a telescope in Hawaii and one in Spain and one in Mexico, they all have different atmospheres over top of them. And each of those atmospheres adds an additional propagation delay that scrambles our signal. And in addition, each of the different atmospheres is also adding a different attenuation as it's going through the atmosphere. And so this is really challenging. This error is really challenging because ideally we would have measured that perfect spatial frequency measurement with an amplitude and a phase. But in reality, it has a random phase on it and also a pretty bad amplitude error as well. And so that looks pretty bad at first. You've lost both your amplitude and phase, so what are you supposed to do? But if you look at it, this measurement, remember every measurement we make is from 2 telescopes. And so if we replace telescope 1 in this measurement equation with telescope 3, then we notice that it has some of the same corrupting terms, G2 and phi2. And so we design algorithms to take advantage of this redundant information across the measurements in order to solve for our images. And so to do this, we developed 2 kinds of classes of imaging algorithms to tackle the problem. The first we call an inverse modeling method. And these methods are very standard methods that have been used within radio astronomy for a really long time. And it's called clean with an iterative self-calibration loop. And this method, it's because it is the traditional method in which images are generally made in this field, it's very understood and well vetted within the community. But these methods were typically designed to work on telescope arrays that have many more telescopes and don't have as bad of noise as we have. And so because of that, they can often get stuck in bad solutions, and you often need a lot of guidance from a knowledgeable user to push it in the right direction. Another type of algorithms that we've been working on more recently, we like to call more forward modeling or regularized maximum likelihood methods. And in these methods, rather than finding an inverse function that acts directly on our measurements to get an image, we instead say, OK, let's try to find an image that when we pass it through some sort of synthetic telescope system, we would get measurements that are similar to the measurements we see and also are likely under some sort of mathematically defined image regularizer or prior that says this one that scores how reasonable each image is. And so the big disadvantage with these methods is that we have to define what is a likely image, and that's really difficult. But the huge advantage of these methods is that we can naturally incorporate all the different kinds of error that we expect to see on measurements from the Event Horizon Telescope. However, even though we've made a huge amount of development in both of these methods, one thing remains is that in both of them, in any method we develop, you always have to inject some sort of information into the problem about what images look like in order to do something with the data. And so we don't, for instance, want to accidentally inject information that the image should look like a ring and then be really surprised that we get a ring back in the end. So we had to be really careful when we were approaching the real M87 black hole data. So the big question we faced when dealing with this data is not just how do we reconstruct the image, but also how do we verify what we're seeing is real. And to tackle this, we actually went through a multi-step process. The first step began years before we even collected data of the black hole. And that was to run synthetic data tests. So we did these through what we call the Event Horizon Telescope Imaging Challenges. And in these challenges, we had a group of people who generated synthetic data, assuming some sort of underlying source model, And they added all the different kinds of crazy air and noise that we expect to see on measurements from the Event Horizon Telescope. This data was then passed off to teams of people who had no knowledge of what the underlying source was. And using their different methods, they were then asked to make their best guess at what the underlying image was. Once this was done, these images were then passed off to a team of experts who would look at the images and come to some sort of conclusion about what they thought the true underlying source was. And this looked a lot like what we actually had to do for the real M87 black hole data. But unlike the real data, we actually had the true image, so we can compare it in the end. So I want to show you a few examples of things we saw in these challenges so you could see how we use these ideas to approach the black hole data. OK, so on the top here is the true images in one of these challenges. And remember, the methods and on the bottom are 5 different methods of people who reconstructed it in different ways independently. And remember, none of those people who were reconstructing those images on the bottom had any knowledge what the true underlying image was. So one thing you notice is, although all of these images look different, they still have some underlying features that are very similar. So a lot of them have this crescent feature. All of them have this crescent feature that's brighter on the left than the right. But there are differences. They have different types of wispy structure coming off of it. So by comparing across these different methods done by different people, you can gain or lose confidence in different features. But we also tested crazy different images. So for instance, we also generated data as if the black hole was actually looking like Frosty the Snowman. And of course, no one in who was doing the data test actually expected something like this. No one expects a snowman in the center of the galaxy. But although the imaging methods weren't designed to work on something like this, hadn't been tuned for these kinds of sources, they were still able to find this underlying structure that looked very similar to Frosty the Snowman. And so that gave us confidence that if we could get something surprising with the real data. We didn't want to just set ourselves up to see what we wanted to see. So based upon these different synthetic data tests, we developed how we were going to approach the actual black hole data. We wanted to avoid this kind of shared human bias like we had done in the imaging challenges in order to assess different features among different independent reconstructions. And so to do this, we split about 40 people up who were involved in the imaging process. Either they developed methods or they're just very good at using these methods, into 4 teams that globally span the Earth. These 4 teams. And these 4 teams, when they were given the data, and they were told, go off and make your best image, but don't talk to each other for 7 weeks. So we all ran into our little respective rooms with our teams, and we worked in isolation, trying to make our best images from the data for that time. And then after 7 weeks, we all gathered together in Cambridge, Massachusetts, and we revealed the images to one another. And this is what we saw. So this was really amazing to me. Although each picture was different, like we saw in the imaging challenges, they all reconstructed a very similar structure. All a ring of roughly 40 micro arcseconds that was brighter on the bottom than the top. And seeing these images was one of the happiest moments I've had in the collaboration. And that's because although we had been able to reconstruct images on our own, it wasn't until I saw that different people using different methods had all reconstructed a similar underlying structure that I really believed the results we were seeing. And without having done this test, we would have never had the same level of confidence we have in our results. But we still wanted to make sure we weren't imposing some additional kind of human bias. We wanted to make sure we weren't trying to get a ring out of the data. And so for that reason, we spent the next couple of months essentially trying to break these images. And that led to the third step, where we tried to objectively choose imaging parameters to remove humans from the loop as much as possible. To do this, we developed 3 different types of imaging pipelines that all had their individual knobs on them that are usually tuned by a human user. And just so you know, you can download all these pipelines online, all the data online, and make your own images too. But instead of having, in this case, instead of having the human tune these methods, we instead said we wanted to search for the best set of knob positions to recover different kinds of source structures. So for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky with no hole in the center. And we found the best set of parameters that allowed us to reconstruct that disk. And then when we transferred those parameters onto the M87 data, we found that although we had tried our hardest to make a disk out of the data told us that there had to be a hole in the center. And by doing this simple training and testing procedure on many different types of underlying source structures, we saw that our methods always preferred this ring shape. And that was true no matter the day that we observed the black hole on or the imaging code that we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them together to form the image that we showed the rest of the world on April 10th. A ring of light, roughly 40 microarcseconds in size, brighter on the bottom than the top. And that is something we really believe in the data. But we still wanted to go through a number of validation tests. And so we went through a number of these, but I'm only going to talk briefly about one of them today. So previously, I talked about how we would find one set of parameters based on some synthetic training data. But why is only one set of parameters reasonable? In reality, there's actually a lot of parameters that would probably give reasonable results. And so we searched an entire parameter space and found all imaging parameters that we thought gave reasonable results on synthetic data. And then by applying these parameters to the M87 data, we could look at the images and look at variations across them to gain confidence or lose confidence in certain features we were seeing. And so, for example, in one of the imaging pipelines, we ran up hundreds of thousands of different simulations, and we identified 1,500 different parameters that we thought gave reasonable results. And so this is an example of two of the parameters that we searched over. The green boxes are showing the parameters that we identified as being reasonable parameter selections based upon tests on synthetic data. And once we had gotten these 1,500 parameters, we could then look across them for variations. So by looking at the standard deviation of the images, we could see what areas we have less confidence in. And you can see along the ring there are regions we aren't as confident about. But this level of confidence is so small compared to how bright that ring is. And so if you look at the fractional standard deviation, you see that we really believe that ring. And it appears in basically all images that we created. But all that wispy structure outside, you really shouldn't believe that. So, we had made these images. It was amazing. But the question, the whole reason that we're trying to do this is we want to learn something about science. And so the question you might have at this point is, did we prove Einstein was right? And well, the short answer is no, but we also didn't prove he was wrong, and that's a big deal too. And so I want to kind of walk you through how we can use these images as a way to understand gravity in black holes. So given a mass of some size, we can calculate the radius we have to compress it down into in order to get a black hole. And so for a short-scale black hole, a non-spinning black hole, this would be its event horizon. This is called the short-scale radius. But actually, we don't generally expect to see the event horizon of the black hole. Instead, we expect to see the photon orbit, where photons are orbiting that black hole before they shoot off towards us. But due to the immense gravity around the black hole, as the photons are shooting off towards us, they're actually lensed to a bigger size. And so we expect to see a ring of light that's 5.2 times the event horizon size for a non-spinning black hole. And when the black hole is maximally spinning, it's just a little bit smaller, 4.8 times that size. And so this is the range of values, the range of diameters we expect for a black hole obeying canonical general relativity. But then notice that this ring size is based upon the mass of the black hole. So if we have a smaller black hole, that ring is going to be smaller if we have a less massive black hole. And that's interesting because actually before the M87 images came out, different methods had predicted wildly different estimates at what the mass of that black hole was. Stellar dynamics predicted about 6.5 billion solar masses, and gas dynamics predicted about 3.5 billion solar masses. And the stellar dynamics really provided an upper limit, so you wouldn't expect a ring any bigger than the yellow one. But then we could ask ourselves, OK, how do we turn this into a test of black holes? Well, wormholes also produce shadow features, but their shadow for the large black hole mass is actually even smaller. And naked singularities or super spinning black holes also produce shadows, but they're even smaller than that. And when you lay the Event Horizon Telescope image on top of them, you instantly rule out all these exotic possibilities, and you're left with a ring that matches nearly perfectly with that of the stellar dynamic measurement of a black hole for canonical general relativity. And so this is one of the many things that we can learn about black holes and gravity by studying this image. But perhaps one of the most amazing things we saw is that by comparing this picture to simulations scientists have done for years, simulations that predicted what a black hole would look like by using their theoretical models and other data from other wavelengths, we find that the image taken actually is amazingly consistent with a number of these predictions. And so by studying this image, we have the best evidence as of yet that black holes exist, as well as a way to study and learn about black holes, how they accrete matter, how they impact their host galaxy. And so we're really just at the beginning. Now that we have this new extreme laboratory of gravity, we're thinking of all the ways that we can use instruments and algorithms to work together to learn even more and to see more around the black hole. And so with that, I'd like, on behalf of the Event Horizon Telescope collaboration, thank you.